Hello, everyone. Welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Kathryn Beck, who currently is a Norbert Wiener postdoctoral fellow at Tufts University. Dr. Beck is an expert on graph signal processing, harmonic analysis, and spectral graph theory. Today she'll be telling us about frames for signal processing on Cayley graphs. Take it away, Kathryn.
Thank you so much, Mike. I want to thank the organizers for the invitation. And also thank you to Mike for his support and mentorship during my talk. I appreciate it. He helped me develop a bit of this, so thanks for your feedback again. Okay, so I'm going to be talking about frames for signal processing on Cayley graphs, which was part of my work for my PhD at the University of Delaware. And I worked on it with Maya Gandhari, who was my PhD advisor, as well as two undergraduates at the time, Skylar Hudson and Jenna Poltenstein. And now I am representing Tufts. So just outline before we move into things. As you can see, there's quite a lot of things going on. We're going to have some motivation from ranked data analysis. Then I'll connect that to Cayley graphs. I'll give you an overview of the graph Fourier transform, which is the main tool in graph signal processing. And we'll talk a bit about frames as well. I'll pose sort of the main question once we have all of this context. And then we'll go into using some representation theory. So I'm going to give a bit more detailed background on representation theory. There will be a part one. This will lead us to a Fourier basis that we can use for Cayley graphs. So some of the initial results. And then I'll give a second part with some representation theory. And then I'll talk about our results with frames for Cayley graphs and some future work. So as you can see, this is quite an interdisciplinary topic and area. We're going to have some algebra, some signal processing, some spectral graph theory, frame theory, etc. So the motivation for this project somewhat comes out of ranked data analysis. So we can think about a ranked choice vote where we have, for example, four candidates from candidate A, B, C, and D, and we're ranking them from our first choice to our fourth choice. So this is a type of voting that's being more widely used in various elections. And we'd like to find ways to try to analyze this kind of data. And I like to work on a lot of problems that involve graphs. So one way we can look at this is how do we reframe this ranked data analysis question of a ranked choice vote? Can we put this data into a graph or network type of model? And so we're going to look at how to do that. In particular, if we have four different candidates, we can think about the different ranked choice votes that individuals will possibly vote for as permutations of 1 through 4. And so we're going to represent those rankings or permutations as the vertices of a graph. So we have 24 permutations of four candidates. So there are our vertices of our graph. And then we want to add edges here that are going to indicate some notion of closeness between different rankings. So we need to make a decision about how we want vertices or rankings to be considered close. And there's some different ways to do this, but one way we are going to think about this is, well, how about we consider rankings to be close together when candidates are just switched in adjacent positions in the ranking. So for example, you can see this 1, 2, 3, 4, this permutation. We'll say maybe it's close to 2, 1, 3, 4, where an individual has just switched the first two candidates. This second ranking, 2, 1, 4, 3, is connected to 2, 4, 1, 3. They've just switched their middle two candidates. And then finally, the last two candidates are switched. So we're going to consider those close because it seems more likely that an individual would be wavering between two different rankings where the candidates are switched in adjacent positions rather than saying switching their first choice with their fourth choice, for example. So if we add all of these edges into our graph, here is the graph that we get. You can see some color labels here in this legend. And I have a bit of different notation going on, so I'm sort of mixing notation. But I have the permutation notation is what's written for these vertices to represent our ranking. And then I'm using cycle notation a little bit as well, but the cycles you see here, 1, 2, 2, 3, 3, 4, are showing just which positions are switched within our rankings and our votes. Okay, so here's our graph that we're working with. And then we want to put a signal on the graph, which is just a function on the vertices of the graph. We can think of that as just the number of people that voted for that particular ranking in the ranked choice vote. And if we label our vertices of our graph, we can think of a signal, this function on the vertices, as a vector. So we're going to think about our signal as a vector in R24 here. So this gives us a way to represent a ranked choice vote and ranked voting data as a graph and a graph signal. In particular, the graph we were looking at is a type of graph called a Cayley graph. And as you might have seen, there was some group structure underlying it. We were looking at the symmetric group on 4 elements. So a Cayley graph is a graph where the vertex set is a group, and then the edges are generated by a set S that's a subset of the group where an edge G is adjacent to H if and only if GS equals H for some S in our generating set. I have another way that you can write this. We'll sort of see this HG inverse appear later on. One thing that we are going to assume is that S equals S inverse, so our generating set is called inverse closed. The last thing I want to distinguish here is that when I say generating set, that's it's a little bit confusing terminology because with groups we have generating sets, so sets of elements that can generate the entire group. This is a different type of generating set. This is a subset of the group that generates the edges of the corresponding graph. So for example, a more basic example is the Cayley graph of Z6 with the generating set of 1 and -1, and that just gives you the cycle graph C6. And then the graph that we just saw is called the permutahedron. And we saw the specific example on 4, on n equals 4. So it's the Cayley graph of the symmetric group with generating set of adjacent transpositions. Okay, so in order to come up with a way to analyze this data on the Cayley graph, we're going to build up to the main tool that's used in graph signal processing, the graph Fourier transform. We need a little bit of linear algebra. We need some matrices to associate with our graphs. So you may already be familiar, but just a reminder, our graph adjacency matrix is a 0, 1 valued matrix where our entry ij is 1 if the ith and jth vertex are adjacent. Our diagonal degree matrix encodes the degree of each vertex on the diagonal, and our graph Laplacian, or the combinatorial Laplacian, is the diagonal degree minus the adjacency matrix. And here we have an example on the right for you to take a look at. So I'll leave that there for a second. Okay. And the nice thing about the graph Laplacian matrix is it's a real symmetric matrix. It has an orthonormal basis of eigenvectors. We can order the eigenvalues, and in particular, if G is connected, we know that the smallest eigenvalue is 0, and all of the eigenvalues beyond that are strictly greater than 0. And in fact, we're going to just assume from now on that we're working with connected graphs. So the graph Fourier transform, this main tool in graph signal processing, what we do, we take our signal in Rn or Cn, And we just expand the signal f with respect to the eigenvectors of the graph Laplacian. So the nth graph Fourier coefficient is the inner product of our signal f with the nth eigenvector of the graph Laplacian. So you can see how this sort of mimics the classical setting of taking the inner products of a signal with the complex exponentials. And in particular, the graph Fourier transform on a ring graph is just the discrete Fourier transform in the classical setting. So here is a visualization of what the graph Fourier transform might do for us. We have a random sensor network on the left with a signal on the vertices that is indicated by this color map. And so the graph Fourier transform takes our signal that's in this vertex domain and it takes it into a frequency domain, much like the classical Fourier transform, where the frequencies in this case are given by the eigenvalues of the graph Laplacian. So how do we use the graph Fourier transform? How can we sort of extract some meaning from these coefficients that we see from the graph Fourier transform? Well, we're going to take a look at that. One way is to think about what is a smooth signal. So I would like your participation on this part, if possible, if anybody would like to share just by looking at this, which graph signal is smoother. I haven't really defined smooth. You could think about it as values that are close together. The function value is in fact closer together. So does anybody have a guess of which looks smoother?
I say B is smoother because
B.
there looks like there's some jumping around on A.
Great. Yes. So A, right, we have like this spot where we go from a very low negative value, we jump to a very high positive value, whereas in general, this B signal is more gradient across, right? We're more similar on neighboring vertices. We have more jumps over here. So just from looking at these, it looks like the one on the right is smoother. Now here's a little bit of a different graph, a random sensor network. We have two different signals. And maybe upon first glance, it's not as obvious which is smoother, but I'm wondering if maybe looking at it a little bit, does anybody have a guess of which might be smoother in this case?
I still think it's the one on the right.
The one on the right. Yes. Any justification?
I'm just gonna say my professional expertise. No, if you look in the bottom right corner, you can see like that little like kind of like pentagon type thing that's all green,
Mm-hmm.
whereas the corresponding pentagon in the other one is like multicolored.
Exactly. Yeah, so this is a good way to look at it. We have this cluster, this region where the neighboring nodes are all almost exactly the same color, but here they jump around a lot more. And that's just looking at one localized region, but we can sort of see on the entire graph, it looks like these are pretty big jumps. There's some smaller jumps here. This one only has really one place that looks like a big jump. Well, how could we use the graph Fourier transform in order to tell us about smoothness? So instead of just sort of looking at the signal, which might be harder to interpret, especially if we have a very, very large graph. So one nice thing about the graph Laplacian that we use to define the graph Fourier transform is that it has this representation, its eigenvalues lambda L. We can write it as the sum over I adjacent to j of our eigenvector chi L entry, the ith entry, minus the jth entry squared. And so whenever we have a smaller eigenvalue of the graph Laplacian, that means the eigenvector, the corresponding eigenvector, is more similar across neighboring nodes. And when we have a larger eigenvalue, the eigenvector is less similar across neighboring nodes. So what does this tell us? If we have smaller eigenvalue components, that means our signal is generally going to be smoother. And if we have lots of larger eigenvalue components, then our signal is going to be less smooth. So we can see our two signals from before and the graph Fourier transform pictured on the right. So as we saw or noted before, the smooth signal was B, and we can see that represented in its graph Fourier transform where it only has a small eigenvalue component. And then we can see a similar thing happening here for our random sensor network. So our B was also the smooth signal. It has more frequency components outside of just the smallest one, but they are lower frequency components compared to the original. Okay, so hopefully this gives you an idea of how the graph Fourier transform can be used in order to sort of interpret different signals on graphs. Gives you some more intuition for that. And moving on, we need a little bit of background on frames as well. Hopefully many of you are familiar with this, but I will remind you again. So our frame, I'm just going to be looking at Cn, is a finite set of vectors where we have positive finite real numbers a and b, where we have this inequality. And A and B are called the lower and upper frame bounds, respectively. Our frame is tight if A equals B, parsable if A equals B equals 1. Here we have an example of a Mercedes-Benz frame, which is 3 vectors in R2. And that one in particular is tight. So that gives you an idea of frames, some reminders of that. And then why do we want to look at frames? Well, we can expand our signal with respect to a frame instead of an eigenbasis. And in particular, since Cn is finite dimensional, any finite spanning subset forms a frame. So we do have to be careful because if any finite spanning subset forms a frame, maybe there are some that do nicer things for us than others. In particular, they can provide stable and possibly redundant systems, which could allow us for reconstruction of our signal from frame coefficients. And also if there's any corrupt or lost portion of the frame, we still might be able to reconstruct our signal. Okay. So with all of that background, we come to our main question, which is in the context of Cayley graphs, or for example, we had the permutahedron earlier. What is a good choice of frame or eigenbasis in this context? So what features of our frame or eigenbasis might sort of capture the underlying structure of that Cayley graph we were looking at? So we have some group structure underlying it. We have this generating set creating all of our edges. So we maybe want something that captures all of that underlying structure of the Cayley graph. And so this leads us to a little bit of background information that will give us one way to approach constructing these frames and bases. So in particular, there's this very nice paper, the signal processing on the permutahedron, tight spectral frames for ranked data analysis by Chen, De Jong, Halverson, and Schumann in 2021. And what they do is construct a nice class of frames for signal processing on specifically the permutahedron. So that's the Cayley graph of the symmetric group with generating set of adjacent transpositions. They utilize the representation theory of the symmetric group, and they're able to show that this frame construction that they use, the coefficients, lead to some nice interpretation of ranked voting data in particular. And so this nice interpretation, while they were using a lot of special properties of the symmetric group, we thought that this could be generalized to the context of a Cayley graph on any group with any generating set, so that this could be used beyond ranked choice voting in particular, or maybe it could be extended even in the setting of ranked choice voting, where you might have a different generating set than just adjacent transpositions. So the question is, can we extend this to Cayley graphs on any group with any generating set? And so that's what we're going to do. In order to do that, we're going to look at representation theory of finite groups to capture that underlying group structure of the Cayley graph. So if you are familiar with representation theory, in particular finite groups already, this part may be quite a review for you, but for those who are unfamiliar and need a refresher, we'll step through some of it with examples so that we're on the same page. So we're going to take our finite group of size capital N. Notice that, or I don't know if I mentioned it earlier, but my size of my graph earlier was capital N. So I'm going to keep them the same, right? Because we're thinking about Cayley graphs, which the vertices are elements of the group. And then this UD of the complex numbers is the unitary group of all D by D unitary matrices over C. And the main idea of representation theory is to take group elements and map them to linear maps or matrices. And in particular, we have this unitary representation of our group of dimension D is a linear map pi from G into the unitary group of all D by D matrices, where it's a homomorphism. So we have pi G of H equals pi G times pi H for all GH in our group. So some basic examples. The trivial representation of a group is a homomorphism that takes all the group elements just to 1. Here when I have C star, that's the multiplicative group of the complex numbers, so it's C without the 0 element. And also, right, I said we're mapping these to matrices. Here, this is a one-dimensional representation, so it's really mapping to like a 1 by 1 matrix, so I'm just writing it. I'm identifying this with the multiplicative group of C, so I'm writing it without the matrix brackets. So this trivial representation for any group, we have this trivial representation. It's a one-dimensional representation. For the symmetric group, we have the sign representation, which takes in our permutation and it maps it to the sign of the permutation. So if our permutation is even, it can be written as an even number of transpositions, then we get 1 from this representation, and if it's odd, we get -1. So this is also a one-dimensional representation. So let's see a higher dimension representation that might be a little bit different than just those one-dimensionals. Okay, so we have Cn, and we're going to take the standard basis, our EIs. The permutation representation of the symmetric group is a homomorphism. It's going to be of the same size as n. So the dimension of the permutation representation is the number of elements that we take or the number of elements in our permutation. Okay, and what do we do? Well, for every single sigma, a permutation in Sn, phi of sigma at our basis element just permutes our basis element corresponding to our permutation sigma. So for example, if we're looking at S3, then our permutation representation is completely determined by the representation at generators of the group, so 1, 2, and 1, 2, 3. And you can see how phi of 1, 2 is just the permutation matrix, the 3 by 3 matrix corresponding with the permutation 1, 2, and similar with the permutation 1, 2, 3. Okay. Representation theory have these unitary representations. So one question then is, can we figure out what the fundamental building blocks of representations are? Sort of like we can decompose groups, we can decompose representations. So we need a little bit of background for that. In particular, a subspace W of CD is called pi invariant if for all elements G of our group. We have that pi evaluated at G applied to W. This space should be a subset of W itself. So as an example, if we consider, oops, sorry, typo, the permutation representation that we had just before on the previous slide, then the following subspaces are phi invariant. In particular, W, which is the span of just the all ones vector, is phi invariant. So you can think about that as radar permutations acting on the all ones vector. It doesn't change anything. We just get something back in that set. And then if we take the orthogonal complement of that space, which is described by the span of all x, y, z, where x plus y plus z is 0. This is also a phi invariant space. So even if we're just permuting again our elements of our vector, we're still going to get that the sum equals 0 and will be in the span. And the way that we use this definition of pi invariant is to give us what are most fundamental components of our representations, which are the irreducible representations. So a unitary representation pi is irreducible if the set was 0 and if the whole space CD are its only pi invariant subspaces. So for example, if we take the permutation representation of S3 that we've been working with, if we restrict it to our phi invariant space W, or if we restrict it to our perpendicular, our complement, orthogonal complement of W, then we get two representations that are irreducible. So the only pi invariant subspaces of those are the set with 0 and the whole space itself. And this is going to lead us into a nice decomposition of our permutation representation in a second. But it actually turns out that if we restrict our permutation representation to the space W, then we just get the trivial representation. And if, in fact, if we restrict our permutation representation to W perp, then we get a special representation called the standard representation of Sn, and we'll see that appear in a moment. But this leads us to some of the core theory in representation theory. In particular, G hat, we're going to denote the collection of all equivalence classes of irreducible unitary representations of G. So there's a little bit that I'm sweeping under the rug here just for the sake of time, but I've sort of had unitary in parentheses, now I have equivalence classes of, so we can just define representations that are not necessarily unitary. They'll map into the general linear group. But then there's a way that you can take a general representation of a finite group and you can turn it into a unitary representation. And you can do that for all representations of finite groups. So this equivalence classes is an equivalence relation coming from the fact that we can make representations unitary or not. So this G hat, just think about these as all of the irreducibles, all of the fundamental components of the group representations. And Frobenius and Shor tell us in the finite case for finite groups that every unitary representation of a finite group will decompose into a direct sum of irreducible representations. So for instance, that permutation representation phi that we had for S3, it decomposes into a direct sum of two irreducible representations, the ones that we saw earlier, those restrictions, in particular, the leftmost one being the trivial representation, and pi here is representing the standard representation of S3. So this decomposition from Frobenius and Shor allows us to decompose any representation, unitary representation, into irreducibles, but there's a special representation that gives us something quite nice beyond that. So if we have a basis for Cn, that's EH indexed by the elements of the group, the right regular representation of G is the homomorphism rho mapping from G into, sorry, this should be capital N, so it's going to have the same dimension as the size of the group itself. And how does it act? Well, it rho at G acts on a basis element EH by taking EH and applying G inverse on the right. So we can think of this as rho G denoting the matrix associated with the permutation H, mapping into HG inverse for every H. Okay. And why is this special? Well, the right regular representation of the group can be decomposed into a direct sum of all of the irreducible representations of the group, each appearing with multiplicity of its dimension. So the right regular representation encodes every irreducible representation of the group, and it also encodes the dimension of every irreducible representation. You may know this as the Peter-Weil theorem in the setting beyond finite groups, but I'm stating it here as such, just since we're working with finite groups. So here's an example. Here's our group S3 again. And we had some representations from before. We knew that there was this special representation of S3, the permutation representation, that decomposed into the irreducible of the trivial and of the standard representation. But we also know that every single symmetric group has the alternating representation, which is a one-dimensional representation and thus is an irreducible representation. So these are all of the irreducible representations of the symmetric group S3. And so by the Frobenius-Shor theorem, the right regular representation of S3 can be decomposed into this direct sum of these irreducibles with the multiplicity of their dimension. So in particular, you can think about this for each element of our group, that rho of G can be block diagonalized and look like this following matrix. So we have a 1x1 block with the trivial representation at G. We have a 1x1 block with the alternating representation at G. And then we have this 4x4 block composed of two 2x2 blocks containing the standard representation at G. So this is a very nice feature of the right regular representation that it encodes essentially this entire group representation structure just in one representation. So now, with all of this representation theory, this right regular representation, how does this connect back to Cayley graphs? Well, for a Cayley graph on the group G with our generating set S, it turns out that if we think about our adjacency matrix of the Cayley graph, we can write it as a sum over all of our generating set elements, S, of our right regular representation, rho, evaluated at S. And where does this come in? Well, we can maybe think about here that rho, right, or right regular representation, is encoding this permutation H mapping to Hg inverse. And if you recall from our definition of the Cayley graph, towards the beginning, we had how our edges are constructed in our graph, right? And they were constructed in the following way, where Hg inverse was an element of our generating set S. So our adjacency matrix has this very nice way that we can write it in terms of the right regular representation. And we can push this further now that we know some more about the right regular representation, that it encodes all of the irreducible representations. So in particular, as we had just said, the right regular representation can be block diagonalized or written as a direct sum of all of the irreducible representations of the group with multiplicity of their dimension. And then if we just rewrite this a little bit, going to bilinearity, I can look at this sum. And so now my adjacency matrix of my Cayley graph is just a direct sum of dimension of the irreducible representation of the group times this special matrix, which is just the sum over all of my generating set elements at pi s. So in particular, we can block diagonalize the adjacency matrix in this way, similar to sort of what we saw before, but this time, so this pi of capital S is this sum over all little s and capital S of pi s. Okay, so I have this nice way to block diagonalize my adjacency matrix of my Cayley graph in terms of all the irreducible representations of the group, and it's also encoding this structure of my generating set as well. And so here we have this captured. This gives us a way to create a basis for signal processing on our Cayley graphs. So let G be a weighted in parentheses. I've left out another layer of this, which is that you can put a weight function on the edges of your Cayley graph and generalize this one step further. But for now, let's just think about an unweighted Cayley graph defined on a finite group with our generating set S. S should be inverse closed. And we have this special matrix pi capital S, which is the sum that we saw before. And so the eigenvalues of the adjacency matrix are just the eigenvalues of all of these pi S matrices union over all the irreducible pi's. The eigenvectors can be explicitly described in terms of eigenvectors for pi S for all the irreducibles, which I'm leaving the details out here so that we can see specifically our orthonormal eigenbasis. So how do we construct our eigenbasis for AG? Well, for each irreducible representation pi, we're going to fix an orthonormal eigenbasis for the eigenspace of pi s. This is Q pi s. And we can, I have this a little bit backwards. I will tell you what these are in a second, the pi ki. But you can think about them as linear combinations with coefficients in the eigenspace of pi s. And I will tell you what the pi ki are here in just a second. So, but how is this useful? Well, in particular, if we think back to our initial graph, our permutahedron, where we had the P4, it had 24 vertices, and its adjacency matrix was this. So it's quite large already for just having n equals 4. We end up having 24 by 24 matrix. So you can see as we go with larger and larger amounts of candidates in a ranking, our matrix is going to get quite large. And this theorem tells us we can block diagonalize our adjacency matrix like this, where the irreducibles of S4, we have those two that we saw before of degree 1. We have 1 of degree 2 and 2 of degree 3. So really the eigenvalues and eigenvectors and eigenbasis can just be computed based on that of all of these smaller matrices. And the largest size of these matrices is of degree 3. So the largest matrix you have to compute an eigendecomposition for is a 3 by 3 matrix. Okay, and how do we get into frames and that thing that you saw before that was undefined, which is called a coefficient function? And so a coefficient function maps from our group into the complex numbers, and it takes our representation pi at G, applies it to a vector C, and then takes the inner product with eta. And so whenever we have a standard orthonormal basis for a space, we can rewrite our coefficient functions where instead of C and eta, we're just taking our coefficient function with respect to this orthonormal basis. And what this represents is a matrix entry of the representation pi at G represented in this same basis. So sometimes you hear these stated as matrix coefficients. Okay, and the coefficient space, so the coefficient function space, e pi I, we're just going to take all the coefficient functions and we're going to fix the second index and vary over the first index. So Frobenius-Shor theorem, not only does it tell us about the right regular representation decomposing, but then it gives us this nice way to decompose our space into a direct sum of these coefficient spaces. And it allows us to write an orthonormal basis for our space Cn. This will inspire our frame construction. So in particular, we define a class of frames called Frobenius-Shor frames, where each atom belongs to one orthogonal component of the Frobenius-Shor decomposition. So each of our frame elements belongs to just one of these orthogonal spaces in this decomposition. And then how do we connect this to what we saw earlier with our decomposition of our adjacency matrix for a Cayley graph? Well, we're going to define this space. You can see it was similar to what we had before for our eigenbasis for our adjacency matrix. And in particular, we're taking linear combinations of our coefficient functions where our coefficients are in the lambda eigenspace of that matrix pi S that we kept seeing appear in the decomposition of the adjacency matrix. So with this context in mind, we're going to define a Cayley frame, which is very similar to the Frobenius-Shor frame that we saw before, but now it's with respect to this new space Z pi I lambda. So a frame for Cn is an S Cayley frame if for every atom there is an irreducible representation, an eigenvalue, and an index so that that atom is in the corresponding space. And how are these related? Well, it turns out that our coefficient space Z pi I lambda, those linear combinations of coefficient functions, that is just a subspace of the coefficient space E pi I. So any S Cayley frame is in fact a Frobenius-Shor frame. And moreover, we can show that there's an orthogonal decomposition of our coefficient spaces even one step further into these Z pi I lambda spaces, so indexed over the spectrum of this pi S. Okay, so what we're going to do is our final step is going to be to give a bit more of a characterization of those S Cayley frames that we just saw based on our eigendecomposition of the adjacency matrix of the Cayley graph. So we need a special map, this theta pi I, which is going to take us from C d pi into our coefficient space E pi I. So really it's just taking our vector and then writing those as the coefficients in the linear combination of the coefficient functions. And it turns out this map is an isometric isomorphism. We also need to look at a restriction to the lambda eigenspace, and the map then forms an isometric isomorphism between our lambda eigenspace of pi s and this special z pi I lambda space coming from the adjacency eigen-decomposition. So, well, how do we construct a frame then in this way? We're going to start with a frame fi pi lambda for an eigenspace E lambda pi s, and we have our lower frame bounds. Then we apply our isomorphism that takes us into our space E pi I, our coefficient space. And in fact, this gives us a frame for our coefficient space where we can describe our lower and upper frame bounds. And then if we union over all of our irreducible representations and our indices of our degree, we end up with a Frobenius-Schur frame, which is also an S-Cayley frame. And we're able to describe our upper and lower frame bounds. So in fact, every S-Cayley frame for Cn is of the form described in 2. So this is our characterization. We can construct all S-Cayley frames in this way, where we're taking frames for these eigenspaces of pi s. We're lifting it up to a frame for the coefficient space, and then we're unioning over all of our irreducibles and their dimensions. Moreover, you have control over some of the different properties of the frames. If you start with frames with some special properties for those smaller eigenspaces, such as their parsable or tight or unit norm, then of course when you're unioning and applying this isomorphism, those properties are preserved in the larger frame. Okay, so why exactly is this useful? Where does this come into the ranked choice vote? Well, in particular, we've given this concrete recipe for the frame construction that was first introduced by Chen et al. In the context of just the permutahedron. So it was a specific group with a specific generating set. And now we have this in the context of any group and any generating set. And in fact, beyond that, which I briefly mentioned before, we can also add a weight function to the edges of our graph. Properties can be preserved, passed from the subspaces to the larger space. And also there is some meaningful interpretation of the ranked voting data. I keep mentioning that. Where does that come in? Well, back to the Chen et al. Paper. For instance, they're able to analyze some different ranked voting data sets. In particular, one is a Minneapolis City Council Ward 3 seat election in 2017. They end up with the permutahedron again on 4 elements, so 4 candidates. They have 5,055 voters. This is what their signal looks like on the permutahedron. And because the frame coefficients are associated with these specific irreducible representations, they're also associated with specific permutations in the context of the symmetric group. And so they're able to extract information based on when there are frame coefficients with higher values or lower values corresponding with these irreducible representations and permutations. In particular, they were able to find things about individual popularity, individual polarity, and pairwise co-occurrence. So in particular, they could see that candidate 3 was generally popular, whereas candidate 2 was generally not popular. They could see this polarity where candidate 1 was often ranked in first or last place, and candidates 2 and 3 were ranked in middle position, so they were less polarizing, and this pairwise co-occurrence where they're ranked together in the first two or last two positions. And interestingly enough, even though Jensen, who was the first candidate, received the most first place votes, well, as they noted, candidate one was quite polarizing, so it did receive a lot of first place votes, but also last place votes. And in Minneapolis, they use an instant runoff voting system, so it's not a plurality, it's not the person who received the most votes, but instead it ended up being Fletcher, the third candidate, who through this analysis we saw was generally the most popular. So that's a whole another can of worms, going into sort of what decides the election. That's a different thing. But this analysis can sort of lead way to interpretation in the context of different voting systems with ranked voting. So I am maybe a few minutes over, so I think I'll wrap it up here. Here's ongoing future work, apply to more data sets, and I have some applications of this and some other sort of combinatorial frame-like areas. Here are the references. So the Halverson, De Jong, and Schumann paper is here, and then this one is the newer one where we have the weighted version, and this has the unweighted version. Thank you very much.
All right, let's thank Kathryn by pressing some buttons.